Hi everyone, my name is Nikhil, Assistant Professor, Department of Mechanical Engineering, Jyoti Engineering College. In this presentation, we are going to discuss about the expression for crippling load when both the ends of the column are hinged using Euler's column theory. So these are the learning outcomes. Now what is actually a compression member? A column or strut is a member of structure which is subjected to axial compressive load is considered as a compression member. Now what are the differences between a column and a strut? We already discussed this topic in my last video, so you can go through that. Now the failure of a column may occur due to buckling, as in the case of long columns, and in the case of a short column, if the material is ductile, the failure may be due to compression, but if the material is brittle, the failure may be due to shear. Now these are the assumptions made in the Euler's column theory. We already discussed this in detail in my last video. The assumptions and limitations of Euler's theory we already discussed, so you can go through that. Now failure of a column. As I said earlier, in the case of a short column, the failure may be due to compression or shear. So the expression for compressive stresses, we have sigma C equal to PC divided by A, where PC is the compressive load acting on the column and A is the area of cross section. But in the case of a long column, it may fail due to buckling. So expression for buckling stress is sigma B equal to P into E divided by Z. So here you can see the figure, and the dotted lines represents the initial condition of the column, and due to the force applied, you can see on both ends of the column force P is acting, and after the force applied, the column may bend like this, and B was the initial midpoint of the column, and after the load applied, it is deflected to this much distance, and that distance is represented as small e, and here L, capital L, is the span of the column. So we have the formula for buckling stress, sigma B equal to P into E divided by Z, where P is the load applied, E is the maximum deflection at the midpoint of the column, and Z is the section modulus. Now the sign conversion. So a moment which will bend the column with its convexity towards its initial center line is taken as positive. Here you can see in the first figure, it represents the positive condition. But a column which will bend the a moment which will bend the column with its concavity towards its initial center line is taken as negative. So the negative condition is represented in the second figure. Now what is crippling load? This also we have discussed in my last video. Crippling load is the load at which the column just buckles. Now we can move on to the expression for crippling load when both the ends of the column are hinged. So here you can see the column, and after the load applied, that is at the two endpoints of the column load P is acting, and due to the application of the load, the column is deflected like this, and the deflected column is represented as represented by the curve ACB. So ACB is the buckled column after the application of load P at both the ends of the column. So consider the column AB of length L and uniform cross-sectional area A hinged at A and B, where P is the crippling load at which the column just buckled. Due to crippling load, the column will deflect into a curved form ACB. And now consider any section at a distance x from the end A. Let y equal to deflection or lateral displacement at the section. So here you can see from end A we are considering a section at a vertical distance of x from the lower end of the column, and corresponding to that point the deflection of the column is represented as y. So y equal to the deflection or lateral displacement at the section. So the moment due to crippling load at section equal to P into y, but here you can see a negative sign. So as we discussed earlier, here the column is bending like this. That's why we put a negative sign to this equation. Okay, now mathematically we have the equation for moment, which is equal to EI d square y by dx square. Now we can equate the expression for moments. So EI into d square y by dx square equal to minus p into y. Rearranging the equation, you will get EI d square y by dx square plus py equal to 0. Now we can divide the equation by EI. So you will get d square y by dx square plus p by EI into y equal to 0. Now that equation can be written as d square y by dx square plus alpha square into y equal to 0. That we can take as equation number A, where alpha square, which is equal to p by EI, or alpha equal to under root p upon EI. Now the solution of the equation, the above equation, is y equal to c1 cos of alpha x plus c2 sine of alpha x. Now substituting the value of alpha in the above equation, we have y equal to c1 cos of x into under root p by EI plus c2 into sine of x into under root p by EI. That is equation number 1. Now we have two end conditions here. From the figure you can see that at point A the value of x is 0, corresponding value for y is also 0. Now moving to the upward direction, the value of x is increasing, but the value of y, it is in the initial stage it is increasing up to the midpoint, and from the midpoint to the upper end of the column, it is gradually decreasing. So when the value of y reaches at point B, it will become 0. So at point at the end B, the value of x is equal to capital L, and corresponding to that, the value of y is equal to 0. Now we can take the first end condition, that is at point A. As I said earlier, at point A, x equal to 0 and y equal to 0. Now putting these values in equation number 1, we get 0 equal to c1 cos 0 plus c2 sin 0. And finally, we will get c1 equal to 0, and that is considered as equation number 2. Now, the second end condition, that is at point B. At point B, the value of x equal to capital L and corresponding value for y equal to 0. Now substitute these values in equation number 1 and solving the equation, you will finally get 0 equal to 0 plus c2 into sine of L into under root p by ei. That is considered as equation number 3. From the above equation, either c2 equal to 0 or sine of L into under root p by p upon ei equal to 0. As c1 equal to 0 and c2 equal to 0, then from equation number 1 we get y equal to 0. That means there is no bending for the column. So such a situation is not true. So we cannot consider that condition. Therefore, we can consider the second condition, that is sine of L into under root p by ei equal to 0. In order to satisfy that condition, the value of L into under root p by ei equal to either 0 or pi or 2 pi or 3 pi. Now taking the least practical value, we will get L into under root p by ei equal to pi, and rearranging the equation, you will get p equal to pi square ei divided by L square. So that is the expression for crippling load when both the ends of the column are hinged. This formula is very important. So you can expect problems from this session, and there is also questions from this session to derive the expression. Thank you.